Hello everyone, you're welcome to this channel once again. Today we have a peculiar question from the thermodynamics point of reference, specifically on e-transfer. Now let's read through the given question. An electric hot plate is maintained at a temperature of 350 centigrade and is used to keep a solution just boiling at 95 centigrade. The solution is contained in an enamel cast iron vessel of wall thickness 25 mm and enamel thickness 0.8 mm. The heat transfer coefficient for the boiling solution is 5.5 kilowatt per meter square Kelvin, and the thermal conductivity of the cast iron and the enamel are 50 and 1.05 watts per meter Kelvin, respectively. Now, calculate the resistance of the heat transfer, which is 1 over U for the unit area, and the rate of heat transfer per unit area, which is Q dot. Once again, an electric hot plate is maintained at a temperature of 350 centigrade and is used to keep a solution just boiling at 95 centigrade. The solution is contained in an enamel cast iron vessel of wall thickness 25 mm and an enamel thickness 0.8 mm. The heat transfer coefficient for the boiling solution is 5.5 kilowatt per meter square Kelvin, and the thermal conductivity of the cast iron and the enamel are 50 and 1.05 watts per meter Kelvin, respectively. Calculate the resistance of the heat transfer for the unit area and the rate of heat transfer per unit area. Now, how do we approach this particular problem from a thermodynamic reference? First of all, we were given an electric hot plate which is maintained at the T1 temperature, that is the first temperature, 350, and we have the solution boil at 95 degrees centigrade. Now, by pulling out all the parameters given in this particular question, we have our T1 350, our T2 95 degrees Celsius, and we have the thickness of the enamel 0.25 mm, which gives us 0.025 m. We have the thickness of the enamel thickness, which is 0.8 millimeter, which gives us 0.0008 meter. And we have the coefficient of heat transfer for the boiling solution, which is 5.5 kilowatts per meter square Kelvin, which becomes 5,500 watts per meter square Kelvin. We also have the thermal conductivity of the both cast iron and the enamel, which are given. Now, how do we calculate the total thermal resistance? by using the formula based on Fourier's law, which is given in this caption. Now, the total thermal resistance for the heat transfer is 1 over U equals 1 over lambda plus x1, which is the thickness, over lambda 1 plus x2, which is the second thickness, over lambda 2. Now that we know all our parameters, we can slot it in this particular equation. That gives us 1 over U equals 1 over 5,500 plus 0.025 over 50 plus 0.008 over 1.05. That gives us the total thermal resistance, 1 over U equals 1.44 times 10 to the power -3 meter square Kelvin per watt. Now that we have found the total thermal resistance, while heat is transferred from the hot plate to the enamel and the cast iron vessel, now we can find the final problem, which is the rate of heat transfer. By using the formula for the rate of heat transfer, which is dot Q equals T1 minus T2 over 1 over U, that is the temperature gradient over the total thermal resistance calculated. So that gives us 350. That gives us 350 minus 95 over 1.44 times 10 raised to the power -3. That gives us 176626.69 kilowatts per meter square. Watts per meter square, and definitely our final rate of heat transfer becomes 176.6 kilowatts per meter squared calculated. Thank you very much.